Where's that camera? All right. So test wise, I picked them up from the scanners. I got the results electronically. There's quite a few people that got 100 on it. So it seems like it was, I don't know, seems like it was, there shouldn't have been any surprises on the test, I don't think. So I will get those in soon. I will have them with me on Tuesday if you want to look at them before class, after class on Tuesday. And yeah, I'll get them in. They were better than last semester's scores. I mean, they look pretty good. So we'll get that done then. And I'll get them here or try to get that in. But I only have one. Now remember, doing your upload, I have one student. The first name is unknown and the last name is unknown. That's actually on the printout. Unknown, comma, unknown. So I do have one. I thought I taught everything, but apparently I did not. But the last test I had like 6 that way. So it's better than the last one, but it does say unknown, unknown. And I have no idea at this point who unknown is. But eventually I will track unknown now. Okay, let's review what we talked about so far. We are doing electromagnetic radiation, and we know visible light is a very, very short part of that electromagnetic radiation. We calculated the wavelength of AM versus FM radio, and we did some calculations. Remember, we are always using, for this part right here, to calculate waves, frequency, wavelength is speed of light is the wavelength times frequency. Okay. Then we looked at, I think we actually, yeah, we did some calculations of the actual energy. So I've said, I don't know, way too many times perhaps, that energy and frequency go together. The higher the energy, the higher the frequency, or the higher the frequency, the higher the energy. So this is on page 6. And then we actually calculated some energy down here. So we left off, we calculated some energy at the bottom of page 6. We're going to continue to calculate a little bit of energy yet, but let's be a little bit more specific on that. What I want to do is, I'm actually going to go to page 11. So on page 11, we know that if we put energy into an electron, we can boost the electron farther into what we say are energy levels, right? Energy levels, certain levels around the nucleus. So if we put energy into an electron and the energy comes back down, we get it back as an emission spectrum of visible light. Now, this Balmer series, notice the Balmer series, everything comes down to level 2. And this is our visible light. This is what we can see. Precipation series, notice it comes down to level 3. This is infrared. We do not see this. And the Lyman series drops down to level 1. This is UV, ultraviolet. So we are going to specifically calculate the energy today that it takes. Now, if it absorbs, it goes up. If it emits, it comes back down. Those are going to be the key words. It absorbs energy when we boost the electron farther out, and when it comes back down, it emits that energy back, and when it emits that energy back, we get visible light. Now notice the colors. Notice this color right here is, let me zoom this out. This is violet, correct? Which one has more energy, violet or red light? Violet, right? It goes in the order of right to bit. Violet light has more energy. Notice it drops farther down, correct? It's no different than you throw a ball up, it comes back down. The higher you throw it, the more energy you're going to get back. So notice that this small drop, it's only a drop on one level, is red light. Okay? So we can boost the electron out farther away and it comes back down. So we are going to actually do some of those calculations and some of those wavelengths and energy. So now we're going to backtrack to page 8. So we go to page 8 here. This light will help me. I think so. So on page 8, trying to interpret the 4 colors found in the emission spectrum. In order to get the emission spectrum, you have to put energy in. It has to absorb energy. Balmer derived an equation relating to 4 colored wavelengths for hydrogen. And those 4 colors for hydrogen are here, here, might be hard to see. There it is. Here, here, we kind of got a slightish green here, and right there's red. So he was able to observe those colors, and then later on, Rydberg went further by developing an equation for wavelength in the visible and not visible region. So here is our Rydberg's equation to calculate wavelength. But notice it's 1 over the wavelength. R is just Rydberg's constant. Now, this is 1 over 2 squared because it comes down to level 2. So this is energy level 2. Then it comes back down to, and this is just a higher energy level. So the higher level can be, 3, 4, 5, and so on. Just so higher than 2, correct? It drops back down to energy level 2. So if you put n equals 3 into this equation, right there, you calculate red at 656 nanometers, and if you put 4 into this equation, we'll get green at 486. Trust me, I punched them all in. But this is calculating the wavelength. So once you calculate this right side, you have to put 1 over that number because you're actually solving it for this wavelength right here. So it's not a difficult equation. You're just putting in what level the electron goes out to and drops back down to level 2. Okay. Now, that picked it out. So I've got, I don't know, probably, I've got hundreds of hours building this like mini textbook. I call it a learning guide. I might change it to a mini textbook. And I've searched hundreds of videos to put the exact one in the right spot. So please, I want to urge you to look at these. This is 6 minutes and 20 seconds, especially for visual learners. It will help a lot. Okay, let's go to the next page. So we know the electron can absorb energy. We know it can come back down. So Rydberg got this equation to work in 1913. Niels Bohr proposed a planetary structure of the atom. Everybody's probably heard of the Bohr model at some time, or Niels Bohr something, in which the electron orbiting the nucleus would emit or absorb a photon if it moved to a different orbit or a different energy level. When the electron in the lowest energy orbit, when the electron is in the lowest energy orbit, the atom is said to be in a ground state. So you have not zapped it with energy. What type of energy are we talking? Usually it's electricity, right? Like what's lighting up this room. Electricity, heat, or light, you can supply energy. If the electron is close to the nucleus where it's supposed to be, it's in its ground state. If the atom receives energy from an outside source, electricity, heat, or light, it is possible for the electron to move to a higher energy orbit, and the atom is now in an excited state. Added energy is absorbed. You're going to hear this word. That's going to be the key word, absorbed. When the electron, or added energy is absorbed, yes. When the electron returns to a lower energy state, energy is released in the form of electromagnetic radiation. The diagram shows the energy states of the hydrogen atom. Again, only the Balmer series is visible. The energies of electrons, energy levels of an atom are quantized, described by quantum numbers, which we will do in a bit. Maybe not today, not sure yet. Integer numbers having only specific allowed values and used to characterize the arrangement of the electrons in an atom. And an electron's energy increases with increasing distance from the nucleus. The farther it gets, absorbs energy, the farther out it goes, right? Again, it's no different than throwing up a ball. It's farther away from the gravitational pull. It's going to come back now with more energy. This is a very good video here, and I don't know if I'm going to play it yet, but it's a really good video in that. Okay, Bohr derived an equation to calculate the amount of energy the electron has based upon which energy level it is in. So here's our equation. This is whatever energy level we are in. And the rest is just constants, huh? There's my Rydberg constant. Here's Planck's constant. And here's the speed of light. Okay, so let's do one of these because Al does this. When we calculate the energy in joules per atom or joules per mole. And notice this numerator is just going to be one value, correct? Those are all constants. So we're going to try to shorten this up a little bit because the numerator is just all constants. So let's see what we're going to do right here. We're at energy level 8. So I'm going to go way over here. So I'm going to put in E8 here. We're doing energy level 8. That's equal to minus, notice there's a minus sign. It doesn't matter where we put it. We can put it right here in the numerator. We've got Rydberg's constant, 1.097 times 10 to the 7. Now, what does this m to the minus 1 mean? The meter is in the denominator, correct? So I'm gonna put it, we know that this meter really is in the denominator, 1/meters. So that's meters to the -1. We've got Planck's constant, which is 6.626 times 10 to the -34 joules times seconds. We've got the speed of light. It's 3 times 10 to the 8th for the speed of light. And we're going to draw our line. That's all over 8 squared, right? Okay, let's calculate this much out. Grab your calculator. In fact, I'm going to grab mine. I want to know what this numerator number is. Let's see, do I have it written down? I do. Let's write that down. This numerator number, let's shortcut it coming up. RHC, what do you get for a numerator number? We get it to the -18 in the numerator. Somebody gets a negative. All right, perfect. I think you should get this. You get 2.179 times 10 to the -18 joules just in the numerator. Somebody else get that exact number? All right, good. So that's not going to change, right? All three of those are constant. We multiply these together. That's these three multiplied together, RHC. All right, then we got to divide by 64 and start getting here. Remember our negative. I think we are going to get -3.41 to the negative 3.41 times 10 to the -20. Good, I see some vertical now. 3.41 times 10 to the -20 joules per atom. Now, for whatever reason, I think the out question, and I probably should have put the exact question up here, they convert this to kilojoules per mole for whatever reason. And we can do that. So I can write it out a little bit better. I think I've got, I don't want to squeeze me too much. Minus 3.41 times 10 to the -20 joules per atom. We're going to change this to kilojoules per mole. And we know there's 6.022 times 10 to the 23rd atoms in a mole. Thousand joules in 1 kilojoule. And I think we finally will get -20.5 kilojoules per mole. -20.5 kilojoules per mole. Okay. Now, if you want the energy change, I've been talking about it absorbs energy and emits energy. So if you want the energy change as the electron moves from a higher level to a lower level, that would be emission, or it absorbs it. It would be the difference in energy in joules per atom. So remember, the energy is calculated for each level, right? So if you wanted to change when it goes up or down, all we have to do, this is a constant, we can factor it out. It's the final level it's at minus the initial level it started. So that would be your change in energy. So we'll do that on the next page here. Let's look at this. Now, this is the electron in the ground state. Energy level 1, it should be in the ground state then. If it absorbs energy, it's going from energy level 1 to energy level 2, right? This is absorbs energy, right? If it drops back down, it emits energy. And if it comes back down to energy level 1, we would not see this. Now, the exact energy it absorbs, is the exact energy it releases, just equal and opposite sign, right? The exact energy it absorbs is the exact energy it releases. So, calculate the energy for the transition of an electron. So I'm going to calculate this one first. Let's calculate this one down here first. Let's see if we can get this value right here. So we're going to start. Let's calculate this one. I'm going to draw my things here. Let's see if we can calculate this. So our change in energy is equal to energy final minus energy initial minus RHC 1 over n final squared minus 1 over n initial squared. All right, we've got a minus RHC. And that RHC, this part right here, is simply 2.179 times 10 to the minus 18 joules. Then what we have here, what's n final? Where does it end up at? Energy level what? Ends up at energy level 2, right? It starts here, it absorbs this energy. So this is going to be 1 over 2 squared minus 1 over 1 squared, right? What I would do is I would just do this first in my calculator. And then multiply it by that. Go ahead and grab your calculator and see what we get. $1.634 to minus 18. Anybody? Yes. Okay, and that's in joules per atom, right? And if we converted that, we would go 6.022 times 10 to the 23rd atoms in 1 mole. And then 1,000 joules in 1 kilojoule. And I think that change in energy to go from level 1 to level 2, we get the number up above. Doesn't this come up to be 984? Or darn close to it? 984. Okay, so that 984 then, what units do we have left? Kilojoules per mole. This is going up, so we know that this is absorbed, right? Now remember on that green sheet, I think, let's see. So grab the green sheet. May want to put it in the way it looks. RAC value. Let's put this on the green sheet. 2.179 minus 10 minus 18 joules. That might help. But it's not that big a deal. You can slam these 3 numbers in your calculator very, very fast too, right? I mean, you can slam those in your calculator really, really fast. Again, those 3 numbers are just constants. So be aware your green sheet's got this on there. It looks like I should add that. Yes. You don't have it on your green sheet? Huh. Yeah, they're on green sheet. I will print out new ones then. I'll print out new ones. My bad on that. I apologize. I'll print out some new ones. That's weird. I must have printed the old version. I'll get you some new ones. Okay. Let's calculate this one up here then. So this is absorbing energy again. So my energy needed to go from 2 to 8. 2 to 8, we're going to end up with minus RHC. 1/8 squared minus 1/2 squared. And my RHC value, we'll just put it right here, huh? 2.179 times 10 to the minus 18 joules. Calculate that. My calculator, I think I would just go 1 divided by, 8 squared is 64. So I think I would go 1 divided by 64 minus 1 divided by 4. I was going to enter that and I'm going to go times. I still have a negative there, negative 2.179 to the negative 18. So we get 5.107 to the minus 19. That's probably the quickest way to do it. And we'll put this in 5 point, how many figs, that's what we say, 107 times 10 to the minus 19 joules per atom. Okay, so again, we're just absorbing energy on the way up, we're emitting energy on the way down, and now we can calculate all that, and we can relate that energy to the exact colors that we see, and that color that we see again has a certain wavelength and hence a certain frequency. Okay. I've got to, let's see. All of this goes together on the next page. And remember, these are always the same. Frequency and energy go together. Frequency and energy always go together. So let's look at the questions that I'll get on with here. Diagrams. Now let's highlight. If it's an emission, it's got to be coming back down, right? So let's do those. Here's emission. So which are your emission lines? This one's coming back down. This one's coming back down. And this one's coming back down. Absorption is going up. So I'm going to switch colors. My absorption here. And absorption here going up. Okay. I always like to get this, I'm always thinking energy for this. So let's see if we can make something right here to kind of help us out. If the energy is high, what else is high? frequency, right? Energy and frequency are high. What's low? The wavelength, right? This should be the greatest distance. Greatest distance. I don't know, distance, the greatest number of levels would be more accurate, but greatest distance is not very scientific. Greatest distance. The more levels it goes. And then the exact opposite. If the energy is low, frequency is low, and then the wavelength is high, right? And this is going to be the least distance. I shouldn't do this in the distance. But that's kind of the key to all these. So we've got an emission line coming down, longest wavelength. So if it has a long wavelength, length is high, frequency should be low, right? And this energy then is going to be the lowest. Energy is the lowest. The lowest energy. Once you get frequency, you can relate it to energy and then just be thinking common sense drops. If the energy is the lowest, it's going to be the shortest distance. So we're looking at E here. Energy lowest, short distance. I'll just put short. Now, the absorption line with the shortest wavelength. If the wavelength is low, what's going to be high? Frequency is going to be high, and here the energy is the highest. And that is going to be the greatest distance. Which is the blue line. There is only, there's only two possibilities here, and the greatest distance, of course, is A, right? Now notice that A goes to infinity. We're going to have a word for that coming up. Completely to infinity. All right, number 3, the emission line with the lowest energy. This one's easy because it's already got it in energy, correct? Then it's the lowest distance. Lowest energy, least distance. That least distance again is E, right? Least distance, lowest energy. The absorption line, oh, it's in energy. Again, least distance up. Distance going up is B, right? The emission line with the lowest frequency would also be lowest energy, right? That would also be lowest energy, emission line coming down. Lowest energy would be the shortest distance again. So we get another E, 3 of them are E. And then the last one. Ionization energy. That removes Basically means it's going to infinity. Completely remove an electron. And then that, of course, is A. If you have the best thing to do is get frequency. Once you get frequency, you have energy, and then you're looking at the shortest or the longest distance. So I've got quite a few of these. 6.4 wave particle duality. I've mentioned it before. Electromagnetic radiation described as both a wave and a particle, photons. No single experiment has yet been done to show electromagnetic radiation behaving simultaneously as a wave and a particle. So scientists now accept this wave particle duality. Okay. I had to put Heisenberg on here, so if you see Breaking Bad, Bryan Cranston. So the Heisenberg uncertainty principle basically is this. We know the electron is moving around the nucleus. And the Heisenberg uncertainty principle is there is no way to know the speed and location at the same time of the electron. No way. So that's basically the Heisenberg uncertainty principle. Now, where do we get all these orbitals and stuff? We're going to talk about Schrödinger. So Schrödinger derives an equation with what he calls wave functions. And wave functions are probability clouds, I will say, probability clouds of where an electron is. So if we go to the next page, not even the next page, let's go to 2 pages in. To this page. Solutions to the Schrödinger equations yields a probability in 3 dimensions for the likelihood of finding an electron about the nucleus. So the question should be, well, we know those electrons are around the nucleus, but what does that really look like? Well, what it looks like are these orbitals. So, to get the ground state, now stay with me now. If you've been on your phone, get off your phone, pay attention. In the ground state, there are 7 energy levels. Every level has an s orbital. This is an orbital. What is an orbital? The region in space that you can find a maximum of 2 electrons. What type of shape is an s orbital? Spherical shaped. How many levels have it? All 7. After that, we need to go to energy level 2. Energy level 2 still has a spherical shaped orbital, but now we also have p orbitals. I would say this is on my y-axis better, but you can have 3 different p orbitals. They're dumbbell shaped. They look like the weightlifting dumbbells that you see here. They're orientated along the 3 axes, the x, the y, and the z. Those start at energy level 2. So from 2 to 7, we've got the p sublevels. These are orbitals again. How many electrons can I put in each orbital? 2, 2, 2. How many total p electrons can I have? 6. And we would write it like that. We put a 6 up above. Now, again, these are probabilities. If you took photographs of where the electron is at any given time and overlaid them on each other, most of the time it's going to be close in here to the nucleus, closer and closer, but then that electron can be farther out. That's the case with all of these. Now we end up with D's. All of these again, what does every shape here represent? An orbital. How many electrons can I put in each orbital? Maximum 2. Now these D's look like they're 4-leaf clovers. Except for this is a dumbbell with a Saturn ring in the middle. Supercomputer calculated according to Schrödinger's equations. But I'm not expecting you to memorize all these shapes and axes. You should know that the P's are orientated on 3 different axes. But if I can put 2 electrons in each orbital, what's the maximum electrons that can go on these blue D's? 10, right? If I can put 2 electrons in each. Then we get these F-shaped orbitals. How many different F orbitals do I have? 7. If I can put 2 electrons in each of these orbitals, what's the total number of F electrons I can have? 14. Now, we know we've got the electrons are going to be in orbitals. Now let's go back to the previous page. Shells of atoms can be thought of as concentric circles, spheres, I want to say, radiating out from the nucleus. Think of the following spheres overlap on each other. Level 1. I make this the size of a BB. What can I put over top of a BB? A marble is bigger than a BB, correct? So now I'm going to put a marble over top of that. What's bigger than a marble? Ping pong ball, right? So here's my ping pong ball. So this is level 1, level 2 that I'll refer to, level 3. I'm going to keep going up. Over top ball, the ping pong ball. I can put a tennis ball, can't I? Level 4 is a tennis ball. Level 5 is a softball. Level 6 is a soccer ball. And level 7 is a beach ball. How many levels do I have? 7, right? So we could say 7 energy levels. Okay. Then there are 4 different orbital shapes designated S, P, D, and F, which is what we just looked at. So now, we have to fill electrons from the lowest energy level to the highest. And this is the off-ball principle. So I have my own way of doing this. The BBs and marbles and everything, I made all that up myself. This is the diagram that we will use. I think it's so easy. So follow me on this, and you're going to draw this out. You're going to do this whole thing just in 2 seconds. So there are 7 different levels. 7 different levels that will cover the entire table of all the electrons. Every level has spherical shape, the S. So we put an S underneath all the numbers. So we go 1 through 7, S, 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 S. Those P dumbbell shaped orbitals start at level 2. So we skip to level 2 and we put P's all the way across. The 4-leaf clover D's start at level 3, so we go to level 3 and we put D's all the way across. These F's start at level 4, we put F's all the way across. Then we draw arrows at about 45-degree angles like this to put the order that they fill. So you can never trust an electron to do what you expect it to do, because you will see that before we put electrons in 4D, we have to put electrons in the 5s, and then it goes back down to level 4. But this diagram will do all that for us. So we're going to go right into that on the next page. So on the next page, so we're going to do this diagram right here in this right corner. Let me draw the sides of it, and then I think I'm going 1, 2, 3, 4, 5, 6, 7. I'm just drawing a line. I put an S underneath all of them. I'm skipping the 2 to do a P. For the rest of them, I'm skipping the 3 to do a D. And I'm skipping the 4 to do an F. Go ahead and do that much right there. 1 through 7, S, 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 P, 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 D, 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 and so on. Then you just start your arrows. They don't have to be straight and perfect. My first arrow is right here. I'm going to fill the 1S. Then I'm going to fill the 2S. And then 2P, 3S. 3P, 4S. Then after my 4S, I got to backtrack into 3D, 4D, 5P, 6S. That right there will do our entire periodic table. Now, you may have seen this done differently. I think this is so quick and easy to do. Yes, some of you, if I just rotate this, it might look like more familiar like this. Not sure, but it's the same thing. This 1 through 7 is our energy level. That symbol is N for our energy level. Our maximum electrons we can do in an S. 2. For P, it's a 6. For D, it's a 10. And for F, it's a 14. So, to identify electrons, we use electron configuration notation, and then hence noble gas configuration notation. But this tells us where the electron is, at what level, sublevel. Now these are called sublevels, S, P, D, and M. Level, and then these are sublevels. Okay, so here's how this works. You have to start here with the leftmost arrow first. Energy level 1. Hydrogen has 1 electron, correct? 1 electron. What level is it going to be? Level 1. What sublevel is it in? It's in an S. How many electrons are there? Just 1. Right? It only has 1. Again, this tells us what level 1 through 7, what sublevel, S, P, D, or F, and the superscript tells us how many electrons. So if we go to carbon, start right here. The first 2 electrons, remember the S can only hold 2 electrons. So when we first start out, we're going to have 1 S. How many electrons can I put there? 2, 1s2. Now, my first arrow is done because I can only put 2 electrons in this S. So now we got to go farther out. We go to level 2 and we start right there at 2s. We got to do this arrow next. So now we have 2s. What am I doing down there? Darn it. 2s. 2. 2s2. Now, my second arrow here is done. I'm going to go on. This arrow is done. I start this arrow. 2p. 2p. How many could I put in here if I needed to? I can go up to 6, right? But I'm not going to put 6 in there. This only has 6 electrons. So far, I've got 2, 4. I only need to put what up there? 2p2, right? So carbon, 1s2, 2s2, 2p2. Now let's do fluorine. Fluorine, we're going to have 1s2, 2s2. Switch it. Quit switching. 2s2, 2p. Run this arrow right here. How many can I put in there total if I needed to? 6. How many more do I have left? 5, right? 5. So I'm just going to go 2p. Right? That's going to be my 9 electrons. 2, 4, 5 is 9. All right. Let's saddle up a bigger horse. Let's go down to 14. 14. Wow, we're saddling up a bigger horse. The Clydesdale's not here. We'll just do this order horse first before we saddle up the Clydesdale. 14. We're going to follow our arrows. Follow our arrows. 1s2 is going to be the first 2 electrons, right? 1s2 is this arrow right here. 1s2. That arrow is done. I'm going to the next arrow. This is 2s2, right? 2s2. We've only put 2 on those S's. Then I start this arrow down here, 2p6. 2p6 right here, 2p6. Okay. 2p6. And I'm going up this arrow, 3s2 right here. 3s2. After 3s2, I'm done with this arrow. I'm going to go to this arrow, 3p. How many can I put in there? 6. I'm going to keep putting, I need to get up to 51 electrons. I'm going to go 3p6. And then I'm going to go 4s2 for this arrow. Let's write it both down. I'm going to go 3p6, 4s2 to finish this arrow that I started. 3p6, 4s2. I'm going to go back up. I've got ways to go yet. So I just completed this arrow, 4s2. Now, after 4s, the electrons go to the 3d right here.
How many can I put in a D? 10, and I'm gonna do it, right? I'm gonna put 10 in here. 3D10. Oops, 3D10. Let's keep going up that arrow. We'll count the electrons coming up. 3D10, then 4p6, right? 3D10, 4p6. Oh, I think we got a ways to go. Let's finish that one. 4p6 and then 5s2, correct? 5s2 is going to finish that arrow. I'm going to count. Now, I'm going to count my superscripts here. I've got 2, 4, 10, 12, 18, 20, 30, 36, 38. I've got 13 more to go. We got 38. Let's go up to our diagram then. After 5s2, the arrow's done. I go down to my next arrow. 4D, right? 4D10. I'm going to put 4D10. 3 to go. I think I said 13, right? 4D10. I got 3 more to go. 4D10, 5P3 is going to end it, right? 5P3. Is it 10, 12, 18, 20, 30, 36, 38, 48, 51? That's it. Again, the electron configuration notation tells us what level, 1 through 7, sublevel, S, P, D, or F's, and how many electrons are in those sublevels. We're going to get more specific coming up. Now let's do this. Somewhere you got this blank periodic table. Go to that blank periodic table. We're going to go to the middle. We're going to duplicate our diagram here. 1 through 7. We're going to do the exact duplicate. Put it about right here. One through 7, S underneath everything. Arrows do not have to be straight. Your arrows do not have to be straight. Okay. This is hydrogen. What's the electron configuration notation for hydrogen? 1s1. It only has 1 electron, right? 1s1. S1. Go to helium right here. How many electrons? Well, how many protons does it have? 2. How many electrons? 2. Helium right here. 1s2, correct? Now going forward, we're only going to write down the ending electron configuration the ending. This is lithium. It's really 1s2. 1s2 is this arrow, and then 2s1. This would end in 2s1, right? Beryllium really is 1s2, 2s2, right? We're just going to add one more electron. This would end in 2s2. After 2s2. After 2s2, this arrow's done. We start this 2p. How many electrons can we have in p? 6, right? You know how many columns are over here? 6 columns. This configuration notation right here. 1s2, 2s2, 2p1. We're going to end in 2p2, 2p3, 2p4, 2p5, and 2p6. After 2p6, I have to start a new row. 2p6, I'm right here. I got to go to energy level 3. I start a new row on my periodic table. I have to do my 3s1 and 3s2 right here. This 3s1, 3s2. After 3s1 and 3s2, that's this arrow. What do we do next? 3p, right? 3p here. So this is going to be 3p1 through 3p6. I know some of you are going to write them all out. That's your personality. You're not going to do the arrow. So 3p1 through 3p6. After 3p1 through 3p6, where do you suppose we go next? This would end in 4s1. This would end in 4s2. That's this arrow's done. Where do we go next? 3d, correct? How many d electrons can we have total if we filled up the d? 10. Wouldn't you know how many middle columns there are in the middle of the table? 10. 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. After 3d10, what do you suppose? 4p1, 4p6. After 4p6, what do you suppose here? 5s1, 5s2. After 5s2, what do you suppose? 4d1. I'm going to arrow that pig over. 41 through 4d10. After 4d10, what do you suppose we got here then? 5p1, 5p6, After 5p6. Six S1, 6S2. Notice table bust down to there. After 6S2, this arrow is done. Notice we got to go to 4F. How many F electrons can you have? 14. Here is 4F1 through 4F14. Now we're gonna rock and roll this out. After 4F14, we come up here, 5D1. 5D10. 6P1. 6P6. 7S1, 7S2. Then we're down here, 5F1. I'm going to arrow it to 5F14 down here. After 5F14, it's D1. 6D10, 7P1, 7P6 does our entire periodic table in the ground state. That does our entire periodic table again in the ground state. All right. Trying to double check quiz questions here. So on this quiz, then there's review problems here, 34 through 50, 34 through 100. It goes to 50. So you should be able to do these quiz questions. All right. So yes, we have class on Tuesday. Yes, we have class on Tuesday. We'll see you Tuesday.